Cool. Yes, that's recording. Okay, so like I was saying, I made a what's called a shell. It's three-dimensional but has zero thickness. So when you're talking about solid distance or anything involving uh, a shell thickness is, or sorry, a shell geometry is something that has zero thickness, but it is in 3 dimensions. Um, so the important is when you save this, you have to save it as one of the compatible file types for Ansys. So if you're building something in SolidWorks, for example, it'll use the native SolidPart file extension, but that's not what we want. Ansys is not compatible with solid parts, so you have to save this file type either solid, which is .x underscore, or you have to save as .igs. And I think you can also do .stp. Usually do IGES files. So I'm going to go ahead and select that. And I'm going to name this part 1, and I'm going to save it to the desktop. So go ahead and do that. Now I'm going to hop on over to Ansys. So when you're searching for the program, it's not actually called Ansys, it's called Workbench, and it's made by the company Ansys. So go ahead and click on Workbench 19. I'll take a sec to launch here. Okay, so what you're looking at here is just, so kind of true, Workbench is a software suite that has a workbench full of tools that you can use. So anything that you here are all different systems that you can use. And then you go down here, you have what's called component systems, and you often hear me refer to ACP pre, and that's what ACP is. It's a component system of Ansys Workbench. So basically, it's a program within a program. And
Got a question. Do you happen to know the
yeah,
difference between the pre and the post?
yeah. So pre essentially processes the setup portion, your composite layups, and you use ACP post to evaluate the results.
So you use both in one?
Yes. Yeah. I think if I remember correctly, yes. I'll know once I get there, but I'm having a hard time figuring it out now. But if I remember correctly, that's the gist of it. So I usually start with ACP pre here. So I just out to this area here, and you can create a standard system. And so this is the basically just the outline of what you're going to have to do. So this top one, number 1, is just labeling what module you have here. And then you can see the different signs. There's a check mark, a question mark that's filled in, and a question mark that's not filled in. So we're going to go ahead and lay it down. So I'm going to double click on each one. So I'll double click on engineering data. And it's going to put the screen. The screen's really messy. So it's important not to get too stressed out when you look at it. So what we want to do is the materials that we're going to be using in the analysis. So today we're going to make something out of carbon fiber and honeycomb. So I'm going to right click in this little blank box here. I'm going to do engineering data sources down here. And just click on that. And it brings up this middle menu here, outline of favorites. And what I'm interested in this top menu here. I scroll down until I reach composite materials. You have general too. It's another commonly used one. But I'm going to double click on composite. And that's going to bring up an outline of composite materials down in the second window here. So, just to give you a quick rundown on the material type abbreviations, epoxy carbon means carbon with an epoxy resin, and UD means unidirectional, and that means that all of the fibers are aligned in the same direction. It's not a woven pattern at all. It's just like, imagine if you laid out 1,000 pieces of string all in the same direction, and they're just held together by the resin. So it's really strong in one direction, but it breaks apart in the other direction. So we don't use unidirectional. That's a bit too specified. We use woven, which has fibers laid 90 degrees perpendicularly to each other. So it has strength in two different directions. And we also use prepreg, which means that there's resin injected into the fabric when you get it. And you guys are both there, so you understand what a wet layup is. That's where you lay the down on top of a dry fabric. But our chassis is made of prepreg carbon fiber, so we're going to go ahead and select epoxy carbon, or excuse me, this one, epoxy carbon woven, so 90-degree orientation, modulus of elasticity of 230 gigapascals, and so we're going to hit the addition tab right here, add to engineering data, and it'll put a little book right there, which means that it's now inside of your toolbar to use later. So honeycomb, we're going to go ahead and add that. It's really important to know that these are generic values that are provided by Ansys, and this by no means represents every single carbon fiber in existence. So there can be carbon fiber that meets these criteria that also has additional criteria, like different densities, different elasticity, stress limits, strain limits, etc. That can all vary depending on the brand of carbon fiber that you buy. We're just going to use the generic materials today. Now you can add custom carbon stuff like that to reflect exactly what you're using, but that's like a later tutorial thing. So we're going to go ahead and save the project. Just hit the save button here, and it's going to make me solve something random. Go to and save it. Okay, so it's been saved. So now we can X out of this window. And you can see we had a green check mark before. We still have a green check. Means we're good to go. Geometry is the next portion. So I'm going to double click on that. Whoops, I should not have double clicked. My fault. I should have right clicked. It's okay. We'll fix that in a sec here. Okay, close out of that. Sorry. So I'm going to find geometry. And I'm going to go down to import. I'm going to browse. Now, like I said earlier, we need an IGES file, and we saved part IGES. So we're going to go ahead and open that. And now we see a green check mark, but we want to go ahead and make sure that our geometry is importing properly. This is really important to do. It might seem like kind of extraneous, but you want to make sure that there's no messed up edges and that it didn't import some weird Chernobyl part. So you can see here it's pretty good. And I should also bring up that when I was in SolidWorks, I merged all these faces together to make sure that they're one part and they mesh all as one part. And I like to go ahead and use the combine tool when I'm inside of this. And this program is called Space Claim, by the way, this little program with the blue outline. I like to make sure that everything's combined. So you can see when I highlight this, all of it turns yellow, which indicates it's all one solid part. And you can just draw a box around it and then click on some random spot and make sure that it is indeed all one part. So I'm pretty happy with that. So I'm going to go ahead and save as. And this is going to change the file extension from an IGES file to a space claim file. So when you change to a space claim file, it's basically just putting it inside of Ansys's native program format, which is okay. So I'm going to keep the same for an extension. Save that to the top. And so now the geometry is no longer an IGES file. It's over as a space claim file, which is good. It works that way. So we got a green check, which means we're good to move on. We're going to go to model and to right click and hit edit. This little M sign right here is important to know. The M is Ansys Mechanical, and that is one of the programs that you can actually scroll down to on here. I'm not going to bother to find it. It is a integrated program you can view your model. So you're going to hit right click, and then you're going to hit edit. And it's going to take a sec to bring up Ansys Mechanical. and just take a little bit of time here. You can see. Okay, cool. So yeah, it's generated our model, which is good. And you can see there's some question marks right here next to the geometry. And this is really, this sign is important to know because the question mark tells you that an action is needed. So your category is geometry and your subcategory is resurface. And Ansys actually goes ahead and highlights portions that need attention. So like right here, it's yellow, which means that I need to assign a thickness to this part. So I need to add a wall thickness. So it's in meters, the units. You can see right here, there's an M. So I'm going to do 1/2 an inch, which converted to meters is 0.0127. So I'm going to go ahead and do that. And you can see nothing has changed. It's just, so we call this the dummy thickness because we're actually going to change the thickness later when we add different plies of carbon fiber. So depending on how many plies of carbon you put on, the thickness will actually increase or decrease. So this is just a dummy thickness to make the program happy. So don't worry too much about this. I just use 1/2 an inch for my own, like, kind of edification. And this is also the stage where we generate a mesh for the part. And the mesh will be used to show results of our simulation. So you want a good mesh, and you want to make sure it's sized properly. I'm going to go ahead and left click on this, and that brings up this mesh toolbar right here. And I'm going to go ahead and click down on the menu and hit generate mesh. And we'll just see what Ansys does. Usually needs some work. Yeah, so looking at it here, you can see it's pretty messy, not very pretty. But the important thing above anything else is that these are continuous connected parts, and they are. All of the little nodes, all the little lines come to really nice intersections here, and that tells me that we're on the right track. So to get more accurate simulation results, think of the mesh as the level of detail. So like the pixels on a screen. So these big, giant boxes right here are not going to give me a lot of detail when I analyze the part. But these small little boxes right here are going to show an increased definition. So you can actually, depending on how big your part is, if it's really big, you don't need to have small mesh cells on big flat walls where anything can happen. But in a corner, we're really interested in a corner because we know stress builds up in a corner. That's just intuition of engineering. So we want a really tight mesh in these corners. Since I'm not really, in the mood to go ahead and adjust the corners, I'm just gonna change the global mesh size. So if you go to defaults right here, I'll collapse the sizing so it's less busy. There's a tab called element size, and again, it's in meters. So you have to be careful to type in your mesh size in meters. So I'm going to do a 1/2 inch mesh size, 0.0127 meters. And now it shows this change, which means, hey, the mesh needs to be updated. It's changed since I last created it. Go up to here in the mesh toolbar and hit update. And it's going to go ahead and take a second here. It's a pretty tight mesh and it's a pretty big part, 1 meter square. So take just a minute. All right, now you can see the mesh is tight. So you can zoom in on parts that you're interested in, like this corner. I'm really interested in this corner. So I'm going to right click and drag the box, and it looks really good, honestly. This is a good mesh. All the nodes match up, meaning that they're nice right angles. And we can see that here, these corners are well together. They all match up. Nothing happening there. So, I'm happy with that. So the next step is to give a name to each face. So I'm going to go ahead and click on each face, and you can see that it's highlighted in green. If you flip around to the other side, the whole surface is green. So I'm going to right click. I'm going to right click on here, and I'm going to create name selection, and it's at the bottom of this drop down menu. So click that, and you can name it whatever you want. I'm going to name it the low X, and I'm going to hit OK. And I'm going to create a name selection on this one by selecting drop down on my right click menu, create name selection. I'm going to call this the low Z wall. Okay. And then I'm going to do this one, and I'm going to do create name selection. I'm going to name this the Y wall. And these shorts, also name if you want to. Also, the difference between panning and zooming. So for and rotating is just click on the center of your scroll wheel, and then if you want to pan, control, and then click the center of your scroll wheel, and you can pan. But side note, I'm going to name these faces. 1, 2, 3, 4. These are all fillets, and I'm doing that by holding down control selecting each one. I'm going to right click, create name selection, and I'm going to name all of these fillets. Okay. All right, so we have green check marks all the way down on our little project toolbar here, which means that we are good to go. You can see I can expand this name selections phase or section, and you can see all of our faces here. So we are doing well. So I'm going to save the project, and it has saved. I'm going to call Ansys Mechanical. Now this little lightning bolt here is the universal symbol for update. So that means that in order to move to the next step, I need to update the project. I'm going to hit update project. And we're running through. Okay, so one exception occurred. So we're getting an error message here. What I do is I usually get this error message, so no worry. So I have green checks all the way down except for setup, which means that we've done everything right thus far. So I need to right click on setup, and I need to hit edit. And it's here. Now this is kind of the meat and potatoes of the program, ACP, which means that now we're really truly getting ACP. Done all the setup, and now we need to start putting our plies of carbon on. So this is just like any other window you can rotate around. It gives you a dummy thickness here. You know, it doesn't mean anything right now because it has 0 thickness at this point. And here it tells you your units too, which is in. So we're going to go ahead and start asking some thickness. So I like to expand material data and expand materials and make sure that I have all the materials here. So this is what we added in that engineering data section. We've got our carbon, we have our honeycomb. So fabrics is your next step. So I like to right click on fabric and do so name. I'm going to name it carbon, or I'm going to name it pre-preg. Excuse me, pre-preg. And we have to assign a material to that fabric, and that fabric is our pre-preg carbon. And our thickness. So I'm going to go ahead and jump for Ansys real quick and figure out what the thickness of a ply of carbon is. Pre-preg carbon ply thickness. And okay, so here, this is a really surface level result, but we're just gonna use it for now. 0.25 millimeters, which is thickness of the one carbon fiber. We'll stick with that, 0.25 millimeters, which means we're gonna have meters. So I'm gonna do 0, 0, 0, 2, 5, and that'll be millimeters. And you can actually price out your part, which is really cool. If you know the price per area of carbon fiber, you can get a final price, which is kind of past what we do. But so I'm going to go ahead and hit apply and OK. So we've got I'm going to right click on fabric again, create fabric. Material is going to be 20. The thickness is going to be 1/2 inch, 0.0127 meters. Apply, OK. And so we've got green check. Now we create with stack up. We're going to go right click on stack, create stack up. And this is really cool. So I'm just going to keep it stackup.1. I don't really care about the name here. And you can select the symmetry of it if you want. You can do no symmetry, even symmetry, odd symmetry. And the layup sequence is top down or bottom up. So I'm trying to remember which is which, but basically it tells you. So I'm going to create. So I'm going to double click on there and drop down and create prepreg. So top down would mean that I'm putting the layer down first, and then each layer after that is, sorry, opposite way. Top down means that this is the last layer, and the last item on this list will be the first layer that I put on. It's really confusing. Bottom up would mean the opposite, that this layer right here is the first layer that I put down, and then at the very bottom of this list, it would be the last layer that I put. But since we're just doing a demonstration, I'm going to keep it as top-down layup sequence, and I'm going to select an angle. So remember that this is woven carbon fiber, so the fibers are already oriented at 90 degrees from each other. So the angle that we're going to choose for each sheet is going to be 0 degrees, 45 degrees, 0 degrees, 45 degrees, which means that we'll have fibers oriented at 0 degrees, 45 degrees, and 90 degrees because they're already orthogonal to begin with. So I'm going to take that one at 0, and this one's going to be at 0. So now I've added 2 layers of prepreg and 3 preg. I'll go and adjust the angles after. 4, 5. Okay, so we've got 5 layers of prepreg, which is probably good for now. Right. So I'm going to change the angles. So it's going to be 0, 45, 0, 45, and then 0 again. So we'll have 3 0 layers and 2 45 layers. Now here I'm going to add our honeycomb, which I misnamed, but it's called fabric 1. That's my mistake. Keep that at a 0 degree angle. It doesn't matter. And then here we're going 5 more layers prepreg. So it's basically we're building our carbon fiber sandwich. And this will just make it easier down the road to apply that places. So here I've added another 5 layers on the other side of the honeycomb. So it's 0 degrees, 45 degrees, 0 degrees, 45 degrees, and then back to 0 degrees. So we now have a symmetrical sandwich. I'm going to go ahead and hit OK. And so you see lightning bolt here. That's because I didn't hit apply. I gotta hit apply, then OK. Now you see the green check mark, which means we're good to go. So sets, this just tells you which different areas are going to be analyzed. There's nothing that I really need to do here, so we can just move on from that. The next important part is going to be rosettes. So rosettes are a local coordinate system. So really important to the program. So right here, this is a global coordinate system, meaning the whole model references this coordinate system right here. You can see. But when you're talking about carbon, we want to orient the carbon fibers differently if we need strength in certain areas or less in certain areas. The orientation becomes really important. And it gets super confusing when you have to reference the global coordinate system, because you have to flip everything in your head, and it gets really complex. So to avoid that, we create local coordinate systems, and those are called rosettes. So you can see right here, it already creates a rosette by default on the space. I couldn't tell you why it does that, but it feels the need. So we're going to go ahead and right-click on rosettes. We're going to start creating some rosettes so that we understand in our heads better how this carbon is going to lay down. So we're going to right-click and then create rosette. And so the screen is a little confusing when you first see it. But if you're familiar with unit vectors, which you probably are in your career, a unit vector is composed of just zeros and ones, and you can add a negative to that to flip the direction. So the origin, we click in this box, or I'm going to say, okay, this wall right here, I want to create a coordinate system on this wall. So I'm going to go ahead and click on the wall, and you can see the origin has changed from 0, 0, 0 to an actual coordinate relative to the global coordinate. So if I went -5 in the x direction, and then I went 0.6 in the y direction, and then 0.14 in the z direction, that's where this would be at the origin. So now these directions are unit vectors. So direction 1 is your, and direction 2 is your y. So currently, if you zoom in on this guy here, and keep in mind this is all referencing the global system right now. Your x direction is positive x, so positive 1, 0, 0, which means that 1, 0, 0. And then direction 2 is your y direction, so it's referencing positive y. With that right now, I don't have any objections to that coordinate system, so I'm going to just kind of let it slide and say that's okay. So I'm going to hit apply, then hit OK. Okay, so now we're going to create another rosette on this surface here. So we're going to do rosette, create rosette number 2, and then you can name them if you want. I choose not to. And then, sorry. And then we're going to go ahead and we're going to hit coordinates that we want there. It can just be arbitrary anywhere on this wall. It doesn't matter. And then direction 1, we have to assign what our x direction is going to be. So I would like to have the x direction be the direction that we build out our carbon fiber. So I'd like to stack it inwards. And so I'm going to go ahead here and reassign the x so that no longer is it 1, but the z direction globally is going to become this local x. So I'm going to hit positive z is local x. And then I'm going to change the y direction. Actually, I'm going to keep the y direction the same. I'm going to apply. And then we're going to put a rosette on the bottom. Although there's one by default, I like to create my own just so that everything's right. So I'm going to create a rosette there. And do the origin here. And then we're going to keep these the same because I don't really object to that. Actually, let me rephrase that. I'm going to change the x to be in the actual global y direction. So now the global y is the x. So, and we're going to keep the z direction the same. I don't know why that one's so big. That's weird. It's like comically big. Okay. Properties, we'll just apply this. Maybe that'll fix it. 2 directions of rosette 3 are too similar. Oh, oops. Sorry. Yep. Okay, that's why. So I made the mistake of making the 2 directions the same. My bad. Let me look at this. So I need y coordinate. So I need an x to be that, and I need z to be hang on, sorry, I'm thinking about this here. So that's x, it's y, and then z is going to be. Huh. Okay, so I can change this to -1. And that should be good. There we go. Okay. Sorry, it took me a sec there. Like I said, it can be really confusing to think about this. But once you set it up, you're good to go. So we've got green check marks all the way down, and we're going to go ahead and move on. So the next thing that you want to create is called an oriented selection set. So we're going to right click here, create oriented selection set. And so it's going to ask you for element sets to reference, and these element sets are up here. So I am going to call this low x wall, and then I'm going to select the low x element set, and it's going to place that right in there.
I'm having trouble connecting to the internet. Take a look at the help section in your Alexa app.
My Alexa, sorry. And then here you can see it's creating this little coordinate system here. Now, this is the direction, this pink arrow, that the carbon is going to be built up on. So I don't want to build carbon that way. That doesn't make any sense. So I'm going to build it in the positive x direction, which is this red arrow. So we're going to change, we're going to keep the point the same. That doesn't matter. But the direction, I mean, you can orient it however you want. But the direction here, you can see now that I've given it a flipped downwards. Well, I want to build inwards. So I'm going to change this negative to a positive. And boom, the arrow flipped just like that. And then we have a rosette. So the rosette that I want to is going to be the last one that I made. This guy right here. You can see it highlights it for you. So we've referenced an element set, a point. We've given it a direction, and we've given it a rosette to reference. We're going to hit apply, and then OK. We're going to go ahead and we have to create 3 more of these. So next is going to be low Z wall, and the point is going to be on the low Z wall globally, which is this one. And again, I want to build inside words, and the arrow is flipped the wrong way. So I'm going to, it's the same as putting a negative, does it for you. And then the rosette, we're going to go ahead and reference the rosette that I want, which is rosette 2, I believe. Right? Yeah, rosette 2. So we're going to reference rosette 2. We're going to hit OK. Apply. Okay. Reference direction computation alternate method. Using. Huh? Hang on. I'm not sure what that means. Just a sec here. Okay, well, seems like it worked. Message vent. We can dissect that later. Okay. Next, we're going to create the oriented selection set for. Also, I'm going to rename this. It's going to annoy me if I don't. It's the low Z wall. Do you guys have any questions so far? I'm sorry, I'm totally just blowing through this here.
So far, it looks all right. I'm just trying to correlate to the one, trying to pick up things what I will be using for like the wall.
Mhm.
So
Yeah, and luckily a wall is a pretty simple shape to make. It'll just be a flat plate, so
should I be able to start that with a shell as well, like this one?
be able to start what? I'm sorry.
Like the start with a shell, then define the thickness later.
Correct. Yeah. So,
Okay.
like you know how we provided a dummy thickness earlier? You'll have to do that as well. But I'll show you how this thickness is actually assigned in a little bit here. I'm gonna have to flip this because I'm gonna put assign and we're gonna select our rosette, and that's gonna be the rosette number 1, I believe. Yeah. Okay. Apply. I don't know why I did this. And sorry about all the noise. It's loud. Modeling group. You need to create a modeling group. Hit apply. Okay. And then we're gonna hit create ply right here. Right click on it.
Yeah, more space.
Okay. So we're creating plies, which is just another step in the process. So we're gonna have to select an oriented selection set, which we just. So this is the low X wall. Click that. Apply material. It's going to be our stack up that we made, which is the sandwich. We're going to hit stack up and apply angle. You can actually adjust your stack up even further and orient your carbon fiber core whichever direction you want, but I don't care to do that, so I'm not going to do that. Don't have to adjust any of these, just leave them as is. And I'm going to hit apply, okay. And then we have to go ahead and do this for the next two. Create ply, oriented selection set, to do the low Z wall. Oops, my bad. Low Z. Maybe not. Oh, yeah, you're right. Sorry. Good
They're
catch.
listening the same.
Good catch. Yeah, so you're going to have to orient selection set, and then apply material. Again, we're going to do the core, which is our stack up, you know. And we'll hit apply, okay. And then we're going to do it one more time. Why is this being difficult? It's giving me a red X. Oh, shoot. Let me redo that. It might be because do I have to create 3 modeling groups? I'm having a reapply after. Let's do that. See if that does anything. Oriented selection set, low Z wall, apply material, stack up, apply. Okay. Yeah, that's fine. That works. So we're gonna do just right click, create apply after. Create apply after. And we're gonna select the low Y wall. Do we have a low Y wall? Oh, we have 2 low X walls. Oh my god. Okay, I've screwed up. Low X wall, that's truly the low X. This is truly the low Z. Oh wow. Yep, we definitely screwed up. That's my fault. I'm sorry. Okay. Let me fix this. So I need to back up just a little bit. So this is actually the low Z. This is actually the low X. This is needs to be deleted. Create new set. Yeah, if you catch me slipping up, don't be afraid to interject on it. This is not a perfect science. A couple mistakes through it. So okay, element sets. We have to select the low Y wall. And then we're going to have to select a point. We're going to have to probably alter the direction. Yep, flip it. Now it's right side up. Rosette. Okay. Apply. Okay. Okay. Now we're going to go back down to our modeling groups. I'll explain this. I'll just kind of fly through it here. Create apply. RNA selection set. Okay. Boom, boom, boom. Low Z. Material. Stack up one. Apply. Okay. Okay. Create. Apply after. And select low X. Apply material. Stack up one. Apply. Okay. Create apply after. Do one more. It's a low Y. Apply material. Stack up one. Apply. Okay. Okay. So we've created all of these sets and everything like that. So you know, we're kind of at the end of the road here. The one last, so I always save this until the end. You don't have to. You can totally do this along the way if you like to. But I like to save the billets until the end. So we haven't done anything with them here. But I would like to create a rosette on the fillets and quickly. And they're a little complicated because they're curved, and that's usually why I save them until the end. It's just less problematic when I can think about it individually. So we're gonna hit the origin, boom. Actually, you know what? Let's not create fillets. We can just leave them as is. This is kind of a preference thing. If, rosettes there, you can, if you want to use the existing ones, you also can. I suppose that's fine. Okay, we need to create an oriented selection set. So I'm going to go ahead and do that. Yeah. This will basically just tell it how to build the carbon on these walls. So for the element set, I'm going to select the billets, point, direction, opposite way, because we can't, again, we want to build in. So we're going to build inwards. And rosette, you can just select whatever you want, because it doesn't really matter. We use rosette 3. Apply. Okay. So hope that works. I may have screwed myself, but we'll see. Anyway, it's about the process. So everything has a green check mark, so we can go ahead and save the project up here, file save project, and finish saving so we can X out of this. And now what we need to do is we want to do a static structural analysis on this guy. So a static structural basically is just it's the module that allows you to put forces on it. So we're going to go ahead and drag structural to create standalone system, and it pulls up this little guy. And setup, we drag, and it'll imply a place that it wants you to put this, and you connect to A5. So I don't have to do all of these above here. It'll fill everything in automatically. And like I said earlier, we have a shell composite, not a solid. This is a shell geometry, so we transfer shell composite data. It draws a little line, and it's filled everything in up to here and eliminated it. So now we have to go through and edit these again. Right-click on model. Oh, sorry, my bad. First I need to hit update because there's a lightning bolt. It's going to see it's got a green check all the way down now. And now I'm saying, okay, hey, I need some input. Check mark, setup, edit, and Okay, so this is a different version of mechanical than we saw. You see some question marks and things like that, and solution information, blah, blah, blah. So static structural, you can right click on this and insert different forces, pressures, bearing loads, anything that you can imagine that condition for a part you can insert. So I would like to insert a pressure. So I'm going to go ahead and I'm going to click on a surface. So see it's highlighted geometry automatically here. It wants me to, so I'm going to select this guy right here and hit apply. So it's applying it to one face, and the arrow tells you the direction the pressure is going to be. Yeah, I'm going to go ahead. It's 1 meter. Let's do like 50 pounds. So I'm going to go ahead and switch over to what's 50 lbf to newtons. 222 point. Okay, take that. Now we're going to. So it's a 1 meter squared area, like I said. So it's going to be this many newtons divided by 1 meter. It's going to be 222.411 pascals. So this is basically nothing over this area. I mean, maybe we'll increase the force a little bit just so we can actually see a result. Let's do like 200 pounds force to newtons. So again, 89.644. Okay. So I'm going to add my magnitude, and it's in Pascal units, 88.9644 Pascal ramped. And you can see this is the pattern in which over 1 second, this one right here, it's going to apply it. You can alter the way in which the force is applied, the time at which it happens, but they just do a linear application for 1 second. So imagine sitting on something, instantly applying, or over 1 second applying 200 pascals. So, okay, so we've created a pressure. We need to fix this somehow. So I'm going to insert a fixed support because otherwise this thing will just go flying through space. So we're going to right click, fix support, geometry apply, boom. That is now fixed on the bottom, and that face will not move at all. So I think I've got everything except for gravity. I want to go ahead and add standard Earth gravity. That just, automatically apply it. However, the direction is not what I had in mind, but that's okay. We'll just keep it that way. Yeah, that's fine. And then solution. So we're going to right click on solution. We're going to do insert. And I want to know the total deformation on the part. So I'm going to do right click, insert deformation total. And I also want to know the strain on the part. So I'm going to do equivalent von misses. And, oh, whoops. It's asking me for more. Okay. Forget that. Just, we'll pretend that's not there. Stress, we'll do equivalent von misses. Maybe not. Okay, it's asking me for more info that I don't know what to give it right now, so I'm just gonna keep this simple. It's composite failure tool, we want that. Now this, if you take like a solid mechanics class, which obviously not everybody's gonna do, but there are different ways to calculate failure of composites than just your normal like metal material. So you're gonna wanna go ahead and click some of these criteria. So the Psi-Woo criteria, to make sure it doesn't fail, it's going to have to pass the Psi-Woo criteria. The puck failure criteria is also a good one to have. They're really well-respected models. Ansys is good to have. And maximum strain and stress, you can turn those off if you want. I'm just going to keep them off right now. Face sheet wrinkling, that just means, hey, is carbon wrinkling up like a piece of skin, like is it going to fail? Core failure, super important. We definitely want to know if our core is getting crushed, the honeycomb core. And, crimping, you can do that. I usually don't. So solution, we want to make sure we've got everything. It looks like we do. So the next to solve it. So right click and then hit solve. And it's going to give me this message, allow access. It'll take just a sec because the mesh is pretty tight and there's a fair amount of force. Cool. Okay, so we've got green check marks here, which means we can view our results. Also, inverse reserve factor is a better measure of safety than the safety factor for carbon fiber. And it's basically a fraction of the stress over the strain, if I remember correctly. Maybe it's strain over stress. But if it's above or below 1, tells you if it's safe or not. So you can see by this that it is safe. It's very safe because it's below 2 or whatever the limit is for inverse reserve. And also these results here can be scaled. So it's not really bending that much. It's just exaggerated so you can see it better. But you can do true scale like this and you can see it barely deforms. So the blue is showing very little stress. But, you know, I'm saying, okay, well, it can really withstand 200 pounds of, or 200 pounds of pressure over 1 meter. So we could go ahead and just, you know, bump it up to like 500, like 1,000 pounds. And we can run the results again, 4448. So we'll go ahead and on here to edit. Pressure. Just gonna change this because I want to see some deformation. The limit that it's going to take us to. We're going to go ahead and do solve. Okay, so we're going to look at total deformation. There we go. So now we're starting to see some deformation, something that actually is appreciable. So you can see the scale right here. And the units are in meters, so that's like 35 millimeters, which is a lot. It's quite a bit. So yeah, now we're actually starting to see the limits of our part. And inverse reserve factor, okay, so it's still safe. You know, it's not going to break, which is good to know. And you know, you can go to solution information here, and this actually prints out an entire report, and it tells you things like the what do you call it? Like the total object moment of inertia. It'll tell you the maximum stresses that it exhibits. And you can print this out and read through it. It's not exciting, I'll tell you that, but it is really helpful when you're writing the mechanical report. So that's good to know. And that's basically the gist of the program. So you go ahead and save the projects and X out. And PJ, you were asking about ACP posts. There's a way to integrate this, but I'm not how. I was trying to think it through. I thought I knew, I didn't. But you can use ACP posts to view more results, which is helpful. But yeah, that's basically the gist of the program. Do you guys have any questions? I know it was a ton of info. Obviously, super exciting.
I had one question. Since that shell I'll be creating is going to be honeycomb and carbon fiber, and I have another part that is not that. So how do you integrate those two?
Oh, so you're saying one part is carbon, one part is not carbon fiber?
Yeah. So could you just like add a plug to the other analysis and then?
So that's a good question. I think it comes assembly. I'm not entirely sure, but that's one thing I wanted to have a meeting about with you and Dr. Kyle. So my goal of this meeting is just to get everybody up to speed on how to use the program, you know, or just at least get them exposed to it, and then hopefully move from here into some meetings with you about how to integrate the two together, because that's not something we've done before, but it's something that we will need to do. So to answer your question,
Also mess with it a little bit, see if I get some.
Yeah, I'll definitely need your help. But yeah, to answer your question, I don't know how to do it yet, but we're going to try to learn it. So yeah. Did you have any questions for me?
Yeah.
I was just wondering how you got from A, like how you got to A to B. Like you're all done with A, the ACP prep, and then you're gonna go to this static structure. How did you get the B like little thing up?
Drag.
Oh yeah, for sure. So they're all drag and drops here, like component. So I dragged pre out and I did the pre stuff, and then I'm going to go ahead and drag static structural out, and I just dragged it here and dropped it. So you can create like a standalone system. I just dragged
Okay.
it. And then setup right here, you can actually drag tabs, and I dragged this over to model and just dropped it.
Okay.
Automatically connects and updates all the information. Yeah, so yeah, that's pretty much how to do it.
Fun.
Yeah. Sorry if it was a little dry, but it was.
It was good information. Like
Yeah.
it's good to know.
Yeah, it's at least good info, you know. So
It sounds simple enough to kind of the vocabulary is used in there simple enough that you can figure it out in the first go.
yeah, once you do it like once or twice, you know, like the first two frustrating, so you'll like forget something. Like you can see, like I've done this 100 times, and even I forgot like one or two things. So, but you know, you get past that. So, yeah, it's cool. Yeah, but you guys have any other questions?
For me, the other side done of the wall.
What's up? Sorry, I couldn't hear.
I'm just gonna try to do this part of the analysis, like do the wall, and see if we can integrate it.
Yeah, yeah, like you were saying, probably just starting a wall to be like just a basic wall without trying to integrate it all the way into the assembly. Just teach yourself ACP pre. Just using something really simple, just a rectangle. Make a carbon fiber rectangle and do some simulation on it just to understand it first, and then it'll maybe be more apparent how to assemble it.
I guess I have another question. I was just wondering why did it only show 3 sides when it was originally like a full box?
Oh no, it was only a 3-sided box.
Oh, okay.
Yeah.
That makes sense.
So, yeah, maybe I didn't make that clear. Yeah, it is a 3-sided box. I just made a random shape to.
Okay.
I was just curious how it would work.
It could look visually as like a box.
Yeah. Yeah, it's kind of an illusion. Yeah. No, it's 3-sided.
Cool.
Cool.
Thank you for doing this.
Yeah, no
Yeah.
problem. Thanks for coming, guys. I appreciate it.
It would be cool if you could upload the recording too.
Yeah, I was thinking. I think we're gonna make a YouTube channel. And I can't remember who it was. And that the other day, I think Bill said something about a YouTube channel. Like he's gonna talk to Ed about it. Yeah, we can put all these on there. That'd be really cool. Good for the team. So,
Yeah.
cool. All right, guys. So I guess I'll talk to you soon then.
Yep. See ya.
Thanks.
Everybody.
Bye.